Let us make it more interesting for you. So again, remember that if you have an element like y in the codomain, there may exist an element in the domain like x with y as their image. If f of x is equal to y, then x is called a pre-image of y or inverse image of y. The set of all the inverse images of y is called the inverse image of y. Symbolically, the inverse image of y is the set of all x values in the domain such that f of x is equal to y. So in this question, we are going to find the image of v and the inverse image or pre-image of w. The linear transformation of the function defined for us is t of v1 and v2. It takes v1 and v2, it takes the first and second component, and it gives us v1 plus v2, and the second component that it creates is v1 minus v2. So let us begin. The image of v is t of 3 and negative 4. Wherever you see v1, you're going to plug in 3. Wherever you're going to see v2, you're going to use negative 4. So you basically say that, hey, now I have a 3 plus negative 4, and then I have a 3 minus negative 4, which becomes negative 1 and 7. So again, your t, your function, which is this function here, for example, takes an element which is v, 3 and negative 4, and map it here to the second set, to negative 1 and 7. Now, how do we find the inverse image of w? By definition, t of v1 and v2 is equal to v1 plus v2 and v1 minus v2, which is 3 and 19. Why is that? Because it says, hey, the output value is 3 and 19. We're just going to substitute that here. But this creates a system of linear equations for us. v1 plus v2 is equal to 3, and then v1 minus v2 is equal to 19. This system is very easy to solve by adding these two equations. 2v1 is equal to 21. So v1 is equal to, 22 divided by 2, which is 11, and v2 becomes negative 8. So basically, you can say that, hey, t of 11 and negative 8 is equal to 3 and 19, or the inverse image of 3 and 19 is 11 and negative 8. So again, this 3 and 19 is located here. 3 and 19 goes to 11 and negative 8. That's how you find the pre-image or inverse image of w. So your w is located here, and your function takes this w and gives you this v, which is 11 and negative 8 in the domain. What is the definition of a linear transformation? Suppose you have two vector spaces like v and w. The function t that takes v and map it to w is called a linear transformation of v into w if it satisfies two properties. The first property is the t of addition of two vectors is equal to the addition of the output values. So basically, if you plug in u plus v, t takes the summation and gives you tu plus TV. Also, it preserves scalar multiplication. So T of C times U becomes C TU. It means that this C can be written outside the function. The function has no changes to C. C stays the same. So a linear transformation is a function that preserves addition and scalar multiplication. Addition in V, and on the right hand side you have addition in W. Just make sure you differentiate these operations. The first operation is in the domain, and the second plus or addition or operation is in W. The same for scalar multiplication. Scalar multiplication in V, and on the right hand side you have a scalar multiplication in W. C times TU. So if you have a function satisfies these two conditions, then you say that, hey, I have a linear transformation. Consider the following function. This function that we worked with in previous slides. This function takes v1 and v2, components of vector v, and it gives you v1 minus v2 and v1 plus 2v2. Now, is this a linear transformation? For this to be a linear transformation, it needs to satisfy two conditions. It must preserve addition and scalar multiplication. So let us begin, everybody. Consider U plus V. U and V are two vectors in V. U plus V is U1, U2 plus V1, V2. You basically take the first components, add them together, take the second components, add them together. So basically you have T over U plus V. So now the input value is U plus V. You need to find the image of U plus V under this function. This is T of U1 plus V1, comma U2 plus V2. By definition, this becomes U1 plus V1 minus U2 plus V2y, because this guy is now substituted for V1, and this guy is substituted now for V2. So you have U1 plus V1 minus U2 plus V2, comma. Now just substitute U1 plus V1 for V1 here, and U2 plus V2 for V2 here, but you have 2 in front of it. So it becomes U1 plus V1 plus 2 times U2 plus V2. This basically is equal to U1 minus U2 plus V1 minus V2. You're just grouping these together, comma, U1 plus 2U2 plus V1 plus 2V2. Well, what is this? This is equal to U1 minus U2, comma, U1 plus 2U2. So this is, I'm just taking the first components and the second component and create the first vector, plus V1 minus V2, comma V1 plus 2V2. So basically I'm adding these two together, but what are these? The first one is your TU, and the second one is your TV. hey, I just showed that this function preserves the addition. I plugged in u plus v, and it gave me back tu plus tv. So the first condition is met. Now for the second condition, I need to check to see if scalar multiplication is preserved or not. So what I'm going to do, I'm going to plug in cu and see if I can somehow factor out c. cu is c times u1 and u2. You basically distribute c into the components. You get cu1 and cu2. Well, T of Cu is equal to T of Cu1 and Cu2. Well, it wasn't that difficult to see. So wherever I see V1, I'm going to plug in Cu1. Wherever I see V2, I'm going to plug in Cu2 into the definition of the function here. This becomes Cu1 minus Cu2, comma, Cu1 plus 2Cu2. Well, this can be written as C times U1 minus U2, comma, U1 plus 2U2. Why is that? Because just a common factor everywhere. I see it here, I see it here, here, and here, and there is no multiplication between these two terms. Or multiplication between these two terms. It's just linear combination. So you can factor out C, and it becomes C times U1 minus U2, comma, U1 plus 2U2. Well, what is this? This is basically C times TU, right? This is how we defined our U here. And then the definition of TU basically says, hey, if I have TU and U is U1 and U2, it is U1 minus U2 and U1 plus 2 U2. So basically the second condition is also met. So for sure you can say that, hey, I have a linear transformation.